So let's consider a specific case of variable coefficient equation. And so let's consider this case, which is called an equidimensional equation. It's also called Euler equation. Euler's name is associated with many things in mathematics, and so don't get confused. This is a particular differential equation, second order differential equation, also associated with Euler. So the form of the equation is written here: x squared y double prime plus ax times y prime plus b times y equal to 0, where a and b are arbitrary constants. So note that y double prime term is multiplied by x squared and y prime term is multiplied by x. And there's nothing multiplying, no x-dependent function multiplying the term involving y. And so if you think about that, that's the reason it's called equidimensional, that we've got two derivatives here and we multiply by x squared and one derivative multiplied by x. No derivative, we don't multiply by anything involving x. All right. So given this, we have a hint that we can, of course, we can establish this very generally, why solutions of this form are allowed, but we can look for solutions in power law form, where we seek a solution y, which is some constant times x to the some power, unknown power r. And so in order to find whether this would satisfy the equation, we need to take derivative. So we take derivative of this, so we simply have this expression, and we take one more derivative, and then we have this factor r times r minus 1 multiplying the relationship. And so we substitute y prime and expression for y double prime and the expression for y in the differential equation and rearrange it. And it's very straightforward algebra. You can see that y double prime, this term, when multiplied by x squared, the power is going to become equal to x to the r. And so that will become r times r minus 1, a times x to the r. So I've just cleaned it up and putting this factor outside. Second term will give rise to this, and this simply gets carried over here. And so the equation becomes this equation. And so if we want to solve this equation and we want a non-trivial solution, meaning that we don't want capital A to vanish, then the quantity in the square brackets must vanish. And so that's this expression that r times r minus 1 plus ar plus b is equal to 0. We can just rearrange that equation and we can see that this is a simple quadratic equation for r. We can solve it and write the two roots for the quadratic equation as r plus and minus in terms of the roots of the quadratic equation with this plus and minus sign and the square root sign involving those terms. And so we have these two roots for the possible values of r. When r is equal to these particular values, then a solution of this form is permitted by the differential equation. And so this we need to discuss further. Obviously, given the form for these roots, there are three cases that we need to talk about. So that's the next thing we will talk about. So we can consider the three cases. If the quantity inside the square root is a positive number, which is true when this condition is satisfied, then we have distinct real roots from that formula, and we're calling them r plus and r minus. And so associated with these distinct roots, we can write the general solution as some arbitrary constant times the first solution involving, say, the plus root here, and another arbitrary constant times the second linearly independent solution involving the second root x to the r minus. And so together they define the general homogeneous solution, and given some initial conditions, we will be able to find C1 and C2. I should note, this is a general statement we can make for Euler equation, that since if you look back at the differential equation, you will remember that x squared multiplies the y double prime term, and therefore x equal to 0 is a singular point of the differential equation. So when we solve for particular problems, we need to keep this in mind. We can't pose initial conditions, arbitrary initial conditions at point x equal to 0. If you try to do that, you will run into a trivial solution with the form of the solution that we're describing here. All right. Okay, so let's consider the other two cases. We have the possibility of the real roots becoming equal. And that would happen if the quantity inside the square root sign vanishes identically, which is exactly this condition. When the coefficients match in this way, then the two roots are equal and equal to this number here. And so then the two solutions, like we had discussed before, they become the same solution. And so that formula gives us only one linearly independent solution, which we have written here in x to the r, where r is the particular value minus a minus 1 over 2. But we need a second linearly independent solution. We have a second order differential equation. It permits two linearly independent solutions. So how do we find the second linearly independent solution? We propose to look for a solution y2 in terms of an unknown function times the known solution, and we can substitute this in the ODE that we have and use the fact that y1 already satisfies the ODE. And then if you go through this algebra, and we had done exactly this kind of algebra previously, you will see that the unknown multiplier function u of x satisfies a very simple equation, which in fact can be integrated. And so that equation would show that in fact the pre-multiplying factor here is log, natural log of x. And so we can define a general solution as this combination. Finally, turning to the case of complex conjugate roots, which is the situation when b meets this condition, then we have solutions involving x to the complex power, a variable x, which is a real number, raised to some complex valued power. And so this may seem a little puzzling. What would be the meaning of x to some complex power? And so we are helped in this by noting the fact that we can rewrite x also as e to the log of x. E to the natural log of x is equal to x. This is sort of the definition of log function, if you like. And so therefore x to the r is simply this quantity here in the brackets is x replaced by e to the log of x raised to the power r. And so then we know the relationship that e to the some power to some other power, this rule for r going up here. So this is exponential of r times log of x, and r is a complex number. And so this is like exponential of a complex number here, which would remind us that if we were to plot such a function, it would correspond to a growing and decaying sinusoid, but not in x in terms of variable log of x. So if we were to plot this against log of x, then we'll have a simple growing decaying sinusoid. Of course, log of x is going to distort the shape of this sinusoid. So anticipating that, let's rewrite this a little further. We can say that the two roots are given by, this was the real part, and the imaginary part, which is given by this formula here, we can call it omega. And so the solution can now be cleanly written in terms of the complex exponential of x. And so x to the minus a over 2, a minus 1 over 2 factor we have taken out, and then we have sine and cosine of omega times log of x. Omega times log of x are the argument of sine and cosine functions. So if we plot this, we would see that these are oscillatory functions whose frequency is changing in x, because as x increases, log of x increases with x more and more slowly. And so these functions stretch out, their zero crossing stretch out, their frequency reduces as x increases. That's the nature of both of these functions. And so the solution is given in terms of arbitrary constants c1 and c2, and then we have to impose initial conditions to find these two constants. So here we have seen the general case for Euler equation described, and so now we want to turn to other equations of variable coefficients, and in particular we will see that there are a number of celebrated differential equations that arise in many science and engineering contexts, and we want to describe those now.